All right, so who got the first one? We've got the limit as x approaches a of f of x equals L, and when it approaches g of x, it's m. If I'm working through those here, what is this first one going to be here? L plus minus. Oh, great, which is really just 2L minus m. If you didn't get that one, refresh from last class. Next one here, 2 times f of x over g of x. The limit of f of x as x approaches a is what?
2L over 2M.
Close?
2L over M.
Yes. Remember, this is not 2 over 2. This is just 2, so it's 2 over 1. So when you're multiplying a fraction, it would just be 2 times the numerators and then the denominators. So 2L over m is the better answer. Amazing. All right, let's talk about limits of trigonometric functions. An analytical approach. So, what's the first thing we always do, actually? Let's just start there. What do we always do? Plug it in. Why would we not plug it in? Because it would go to hell. Because we're dividing by 0. What's going to make this thing divide by 0? There's only one value. It's not a trick question. If I have 3x on the bottom, what would make it 0? 0, thank you. And since 2 pi over 3 is not 0, that means that we can go ahead and just plug it in, like we're smart. So, it means we're going to get sine of 3 times 2 pi over 3 is really just sine of 2 pi. Because we're smart, we can go 3 divided by 3 is 1. Over 3 times 2 pi over 3 is really just 2 pi, because again, the 3's cancel, right? Everyone see how the 3's cancel in both cases? Yes? Were we for real? You guys seem unsure. 3 over 3 is 1 in both cases. Okay, so then what? What is the sine of 2 pi? Unit circle. It is 0. So therefore I get 0 over 2 pi. What's 0 divided by anything? 0. There's my answer. Just 0. All right, over here, is there any way to make a trigonometric function undefined? No. So therefore I can just plug it in. You all right over there? No, you're not okay? Ay, pobrecito, lo siento. Okay, so now, why did I rewrite it this way? Because I think you'll make less mistakes. What is the cosine of pi? Negative 1. So we got 2 times negative 1 squared. So what's negative 1 squared?
1.
Good. Times 2? Amazing. Look at how good we are at this. All right. Each of those was defined no matter what theta was approaching, except 0, I guess, right? However, we know that this isn't always going to be the case, but the limit can still exist. So then what are we going to try and do if we have something where it is going to be a problem? It's going to disappear. Well, let's look at this one, for example. If we look at sine of 0, it's 0. So this thing's going to 0. Cosine of 0 is 1, but 1 minus 1 is also 0. Now, this is a really fancy kind. We like these ones, but we can't do them until we learn more. For now, we're going to have to do some algebra. Later on, we get to do calculus to solve these. For now, we got to do algebra. All right, because it's 0 over 0. But hopefully, you remember some things about trig, and so you can solve this using some fancy algebra. Does anybody immediately see something on there that they should be able to work with?
Sine squared minus 1 equals 2 sine squared.
Kind of. Kind of. I mean, that's not written here, but yes, we're going to use exactly what you're talking about. So the one you should have recognized is sine squared, because, of course, sine squared plus cos squared equals 1, which is the one that Pablo manipulated to give us what he just said. What? You don't think his name is Pablo, or what?
No, we did not learn this.
You didn't learn Pablo's name? How rude of you guys. 100% you learned this one. You may not have learned any others. I can guarantee you learned this one. I can guarantee you did because it's your special triangles. Guys, anywhere on the unit circle, anywhere at all, right? If I draw a triangle, this is a point on the unit circle. This value down here, doesn't matter what it is, it's cosine, right? Right? Good. Okay, what's this one? sine. And what's the hypotenuse always if it's called a unit circle? Unit means 1, right? So it's 1. So this is always 1. So in other words, the cosine value squared plus the sine value squared equals 1 squared, or 1. Okay, so I can guarantee you use this one. You may not have realized it or you might have forgotten, but you definitely used this identity. And it's the one you should never forget. Even my BC students had trouble last week because they forgot this one. Of course, they did a more advanced one, but still. Okay, so we're going to use that. And we are going to manipulate it because we want to know what sine squared equals to. So that would mean that I would need to subtract cos squared from both sides. So 1 minus cos squared theta is equal to sine squared. Now that's super helpful because now I can say, well, the limit as theta approaches 0 of 1 minus cos theta is equal to 1 minus cos squared. Now don't get excited, I can't just cancel one of them, the whole thing's not squared. But I can still do something, because what is 1 minus cos squared? How would I make it easier for you? What's 1 minus x squared? It's a special form of binomial. No. 1 minus x squared. What would we call that? Let's make it easier. X squared minus 9. What would you call that? Somebody said it. Close. Difference of squares. So this is a difference of squares, right? Which means that I can factor it. So I'm going to get 1 minus cos theta over 1 plus cos theta times 1 minus cos theta. Well, I didn't change the numerator. The denominator, this is a difference of squares, so I simply factored it, which you got to be good at in this class. Right, Sophia? Sophia and I did lots of factoring today at lunch. It was great. No, it really is important, you guys. So, like, difference of squares, you should be able to just kind of see, all right? Exactly. So now that means that I can cross out this one with this one. And now my problem went away for me, didn't it? Because now, instead of being a problem, it's going to be the limit as theta approaches 0 of 1 over 1 plus cos theta. What do? Once I've simplified it, I plug it in. So cosine of 0 is, so it's just 1 over 1 plus 1, or 1/2. So what this means is that the function is not defined, right? It has a removable point of discontinuity, right? Or just really what matters is the point of discontinuity. I know it's removable because the limit exists, right? So in order for the limit to exist, what does this mean? This means that at 0, we basically have a function that's doing this, right? Like it's coming together. This is at the point 0. There's a hole there, and then it keeps going. So that's why I know it's a removable discontinuity. Okay?
Why is cosine theta 1?
Why is cosine theta 1? Because what's cosine of 0? I'm not doing cosine of theta. What I'm doing is I'm plugging it in. Once I get it simplified, I take 0, I plug it in. Cos 0 is 1. So that's why I got it.
This is so hard when I have none of the context.
Well, sorry. All right, guys, let's keep it going. We're going to work on some more trig. It's going to be great. I love trig. All right, so right now, what should I do to, like, simplify this before I do anything? Okay, I could just plug it in. I mean, I could make it easier on myself, but sure, we'll just plug it in. Guys, what's tangent?
What? Change tangent.
There we go. Exactly. So it's the same. Hey guys, listen up. Listen up. Tangent is really sine over cosine, right? Yes. And that's fantastic because that cancels and makes my life so much easier. Because now I just have the limit as theta approaches 3 pi over 2 of 3 sine theta. And now it's easier. What is sine of 3 pi over 2? I'll give you a hint. Okay, why was it a problem? Because cosine was 0. So if cosine 0, what does sine need to be? No. 1 or negative 1. If I'm facing down, which one is this? Negative 1. Because it's at 3 pi over 2. I know you guys don't remember your radians very well, but that would be 270 degrees. So we're facing straight down. Okay? If we look at the unit circle, it's straight down.
And we get like printouts of the unit circle.
I mean, I've got a pretty big one on the wall.
You have a Oh.
Sophia felt bad for you guys last year, so she made that. Betancourt.
Oh.
Yeah.
Yeah,
All right, let's keep it going. Let's keep it going, guys. So, next one. Wait. Clearly, this is going to be a problem. It's going to be a problem. I mean, obviously, this isn't 0, but what does secant really mean? 1 over cosine. So, cosine of pi over 2 is 0. So, first thing I'm going to do is rewrite that. So, secant is really 1 over cosine. Yeah, they do. Look at them fabulous cosines going away for us.
And the secant, how did we get rid of the secant?
We didn't. We just changed it for what it is. Secant is really 1 over cosine.
And cosine, 1 over.
Sure. Yes. I mean, you wouldn't normally write it that way, but yes. Okay, and so then at this point I can just plug it in because I don't have any problems anymore. So I'm going to get 1 over 4 times pi over 2. What's 4 over 2? Yes. You're halving it, which makes it 2. I knew where you were going. It's because you're nervous because you got in trouble for trying to steal my BC students. All right. So in this case, the problem is probably going to be sine, but maybe it's cosine. What is sine of pi? What's sine of pi? Sine of pi? 0. So therefore, that's the problem. So we're going to have to try and get rid of it. Let's start by just simplifying. First thing to simplify is literally rewrite everything as sine and cosine. That's your first step always, because sometimes, like in this one, stuff just goes away. So tangent.
Everything cancels out. Sin cos, and then you. Oh wait, no, you can't cancel out those cos, right?
Yeah, you can. So these are going to cancel, which means I have sine over sine. Let's write it in an extra step, just because, you know, we're a little slow sometimes with our algebra. So now those cancel out, which means I'm literally just taking the limit as theta approaches pi of 1. What is the limit of a constant? The constant. Amazing. Boys, do you need help over there? Like, should I send you somewhere?
Wait.
But you're the one that gave me the answer. Don't lie to me. No, it's 1.
Why is the constant 1?
Because what's sine divided by sine? 1. And if I just have a flat line at y equals 1, does it matter what theta is? No, it's always going to be 1.
Cosine divided by sine is 1.
Because anything divided by itself is 1. Pedro, I'm going to ask you to leave real soon, man, just so you can collect yourself. Just so you can collect yourself. All right. So here's what we realized. We tried direct substitution. You should always try it first. It doesn't always work. Then you can simplify it and try it again. If that still doesn't work, this is where then we had to like do that whole like, oh, it's an asymptote left side, right side, right? So what we're going to do here is we're going to learn a couple of, let's call them identities, because for now that's what they are until we learn L'Hopital's rule. So in this particular case here, we're going to look at what happens as we get closer and closer to what number. Look at this chart and tell me, what do you think I'm going to evaluate this for? What am I going to get closer to? So if I'm going this way, I'm getting closer and closer to what number?
0.
So as I get smaller, I get closer to 1. I get closer and closer to 0, right? Same as like this way, I'm getting close. So in both cases, we're getting closer and closer to 0, not 1. All right. Now, I'm not going to make you figure these out because I don't think we have time. I did them ahead of time. But if we plug this into our calculator and we go sine of negative 0.01 over negative 0.01, I'm going to get the value 0.99998. Excellent. 4. If I do it again, but this time at 0.001 negative, I'm going to get 0.9999998. So 6 nines. If I do it again, I think you're getting the point. It doesn't matter. I'm just going to keep adding more 9s, right? So I'm going to add like 2 more 9s. What about if I do it from the positive side? Well, I'm going to get 0.99998. Interesting. And then 0.9999998. And you get the idea. 0.99 whatever, a bunch of 9s, right? So we're getting like closer and closer and closer to what this time? 1. This time we're getting closer and closer to 1. So from the left side, we got close to 1. From the right side, we got close to 1. Therefore, this whole thing, as we approach 0, is 1. So you're going to kind of think of this as like a little identity that's going to help you until we learn L'Hopital's rule later. Okay? Don't worry about it. You got to learn what the derivative is before you can learn what L'Hopital is. Yeah, it's quite a ways away. So for now, we're just going to remember that. And then we're going to identify, like, well, what happens if, like, I have 3 theta over 3 theta? Anybody want to take a guess?
If they approach 3.
0.999. I think that one actually is different. If I remember. Whatever. The point is, it's getting like closer to the same thing.
But it's growing by 3.
I think it is this time. Yeah, I honestly can't remember. But I think yes. I think this time it is like slightly different in how fast it gets there. But the point is, it's still like approaching from both sides 1. Okay. So in other words, what we know is that if we don't quite have this, we can manipulate it to get like the same value in front of theta, and that's what's going to help us. Okay? So that's all we're really learning here, is that we can like manipulate it to make it work. And that's what we're going to talk about in this next part here, where it just says based on this, as long as we have sine of c theta over c theta, and that c is the same number, perfect, this thing just equals 1. Okay? As long as that number is the same on top and bottom. So I guess here, if we wanted to answer it in this spot, like it approaches 1. Like that's what it means. Okay? All right, now, we're going to do it again, but this time with a different one, where we have 1 minus cos theta over theta. Okay, now it doesn't mean it's necessarily going to be 1, so let's actually work it out and check. Obviously, if I'm showing it to you, it is going to like coincide with something. Okay? So if we put in this one, we get negative 0.004999, etc. A whole bunch of 9s. Yeah, there's a 4 in there. I know it's hard to see. If I do it this way, I'm going to get 0.000 and then 4 and then all my 9s. And then if I go to like 1/10,000th, it's going to be negative 0.0000 and then 4 and then all my 9s. And if I do it from the other side, it's going to be very similar, except it's not negative this time. It's going to be 0.004 and a bunch of 9s. Then when I put in my C value as being 1,000th, it's going to be 0.0004 and a bunch of 9s. I should probably do an extra 9. And then if I put it at 1/10,000th, it's 0.0000499, yeah, a bunch of 9s. So what is this one getting close to from the left? What's it getting close to from the right? So 0, right? It's getting closer and closer to 0, right? Because we're adding, like we're pushing the 4999 way further back, meaning it's getting closer to 0. So from both sides, what is this approaching? 0. Amazing, right? So this is the other one that I want you to kind of remember. Okay, for now. Later on, you won't need to. Can you what?
Does it some-
No, it'll always do it.
They go.
Say what?
I don't think I saw the limit statements for a sine theta.
Same thing. 1, 1, and 1.
Just double checking.
Okay. All right, so let's actually try and like apply these a little bit and see if we can figure it out, right? So these two like trigonometric functions that we've just figured out, their limits approach 1 or 0, depending. So we're going to apply some of these things and see if we can figure it out. First thing we always do is plug it in, if I can. Do I need to manipulate this? Can an exponential ever be undefined?
What? Can you repeat it, please? What?
Can an exponential function ever be undefined? Is the domain all real numbers, or is it going to go have a problem somewhere?
Has to have a-
Yeah, all real numbers. What about cosine, a trigonometric function?
Yeah,
Same thing. These are both defined everywhere. So a number defined everywhere times a number defined everywhere is fine, right? So all we need to do is plug it in. So we got e to the power of 0, cosine of 0, not theta, sorry, over 4. What's anything to the power of 0?
1.
What's cosine of 0?
1.
So it's really just 1 times 1 over 4, or 1/4. So if we do it this way, we can put it up here too, I guess. All right, now this time it is a problem, right? Because if I plug in 0, I'm going to divide by 0. Sine's fine, but there's a 0 down here. Does this look like something we just worked with? Like close? What does it look like? Right, so what's the problem? What is it not, like what's it missing? The 4 on the bottom. So it's a good thing that we can be number demigods. We cannot be gods. We cannot just create something out of nothing. But we can manipulate the hell out of it. So that's what we're going to do. Can I always multiply by 1? Always. So I'm going to do that. We're going to take this whole thing here, and I'm going to multiply it by 1. But I'm going to multiply it by a fancy looking 1. So I'm going to multiply it by 4 over 4.
Why did you choose that?
You're going to see. Does it now look closer to what we need? Yeah. Could I write 4 over 4 as like 4 times 1/4?
What?
Could I change this 4 over 4 to be 4 times 1/4? Means the same thing. So what I'm going to do is I'm actually going to take this part of it and put it out here, and this part and slide it underneath. I didn't change anything. I'm still doing 4 times the limit as theta approaches 0 of sine 4 theta over 4 theta. Why can I do that? Well, because if I'm taking the limit of two things multiplied, we already talked about it, it's just the two limits like multiplied together, right? And what's the limit of a constant like 4? It's just 4. So I might as well just pull it out and deal with like multiply by 4 later. So now I can work out this though, because what is the limit as theta approaches 0 of sine 4 theta over 4 theta? It's 1. So this is really 4 times 1, or just 4. Does that make sense? So the key, you guys, here is that I cannot create something, but I can manipulate it. And the way that we usually do that in math is multiplying by a fancy looking 1. No, but I can do it again in the next one and then explain it again. Okay? Because it's the same idea. Okay. So this one again looks similar, but it's not quite working. And if I plug in 0, it all goes to hell. So I need it to be sine 2x over 2x. So I need a 2 on the bottom, and I need to get rid of the 3. Well, thankfully, the 3 is a constant, so what could I do with it? I can just bring it outside, right? Like basically what you need to realize is I could rewrite this as the limit as x approaches 0 of 1/3 times the limit as x approaches 0 of sine 2x over x, right? We learned that like way back when we talked about like in lesson 1.4, which I guess was just last lesson, the properties of limits. We can do that, right? Great. What is the limit of a constant? It's just the constant, so I don't need to worry about it. So instead of doing this, because I'm not going to lie to you, I don't ever want to see you write this step. This is like a waste of your time. Because what you actually need here is you need a 2 on the bottom. So instead of writing like 2 over 2, I'm going to write the 2 here and the other 2 here. Right? It's still just 2 over 2. Would you agree that all I did is multiply by 2 over 2? Yeah. I just put the 2 on top out here and the 2 on the bottom there. Why did I do something like that? Well, because this is what? Remember, we just did this identity. What is it? The limit as x approaches 0 of sine 2x over 2x, it's 1. And the limit of a constant is the constant. So my answer is just 2/3. Are you all with me? You didn't understand why I pulled out the constant? Because, guys, anytime you have a constant, you should be thinking, this is a waste of my time. It's the constant times the limit. Because I pulled out the, if this is like 3 on the bottom, that's 1/3. So I'm pulling the 3 out of the limit because it's a waste of my time to have it there. Right? Like, it's the same as when we learned it yesterday when we talked about the most basic form. We did the limit as x approaches whatever, doesn't matter, of c times something. And we said we could just pull the c into the front. Well, c in our case here is just 1/3. So I'm just going to pull it out front. I can always put the number in front because the limit of that constant doesn't change anything. That's what I said. I don't want you to write it this way in the future. It's a kind of a waste of your time. Yeah, Amelia. Because what do I need? I needed to create this. Remember? I said we can be demigods. We're number demigods, which means we're going to manipulate the heck out of things. We're going to do algebra. I multiplied this whole thing by 2 over 2. All I did is I put this part of the 2 here and this part of the 2 there. Because if they're all multiplied, it doesn't matter what order I multiply in. It doesn't matter where they are. As long as I'm still multiplying by only 1, which is 2 over 2. I mean, you could, but it doesn't really change anything. Because what's the limit of a constant 2? 2. Right? Doesn't change anything. So look at this one. What is the numbers that I don't need? What's the coefficient that's annoying? The 3 on the bottom and the 2 on top. So I'm literally going to start by just rewriting this as like 2/3 times my limit as theta approaches 0 of sine of 5 theta over theta. Now what's the number I'm missing? The 5. So I need to multiply this by 5 over 5. So I'm going to multiply it by 5 over 5. But I don't really need the 5 here. I need this 5 to be there, right? So I'm going to algebraically do that. I can put it inside. So 2 times 5, I'm going to get 10 over 3 times the limit as theta approaches 0 of sine 5 theta over 5 theta. And now what is this? What is the limit as? It's just 1. So I got 10/3 times 1, or just 10/3. There's one more. 10/3 times 1. Yeah, that's time. Sorry, I know it looks like a minus sign. Should be. All right, our last one. This time our problem is the 0 that's actually there. So I'm going to have to do a whole bunch of algebra. So I'm going to have to break this up. I'm going to think of this as the limit as theta approaches 0 of sine theta over cos theta over theta. Then, how do I get rid of a fraction of a fraction? Keep, change, flip. Well, yeah, you can think of this as over 1. That's fine. That's part of it. So I'm going to get sine theta over cos theta times 1 over theta. We're getting somewhere, right? Isn't that sine theta over theta close? It's close now. So then what I'm going to do is I'm going to split apart those two fractions, and I'm going to write them differently. So the limit as theta approaches 0, I'm going to get sine theta over theta times 1 over cosine of theta, All I did is change the order I multiplied in. That's fine. We're allowed to do that, right? Commutative property. And then, can't I just take these two limits separately now? Yeah. So I'll write it out, even though I don't technically need to. This is like sine theta over theta times the limit as theta approaches 0 of 1 over cos theta. Y'all with me still? Yeah? Because remember, properties of limits, if they're multiplied, it's the same as taking them separately. I would never write this step. I'm doing it to help illustrate it for you to make it easier to see. Okay, but I would go straight to my answer normally. Yeah.
So sine theta over
One
theta
sec, one sec.
is 1, and then 1 times 1 over cosine. Then we can input the 0, which
Yep.
will give us 1.
1, right? Because now at this point there's nothing wrong, so I just plug in 0 to cosine. I get 1. Cosine of 0 is 1. So this is also, ooh, that's a terrible bracket. This is also 1. So I get 1 times 1, or just literally 1. Amazing, right? Amazing. And guess what? We've got 4 more, but we're going to do them on the whiteboards. Okay? So we're going to stop there. I'm going to have you guys do these ones on the whiteboards, and we'll see how you guys are doing. We'll give each of you one.